So thank you very much for being here. I'm super grateful that I'm here to give this talk today. So I'm going to tell you about a project that I've been developing with my supervisor, Carlo Contaldi, at Imperial for the past 3 years now on making maps of the gravitational wave background. So the first half, roughly, of this talk will span the work that we've done with ground-based interferometers and analyzing data from the LIGO detectors. So for reference, these are the 3 papers I'm going to be referring to. And then in the final part of the talk, I'll be telling you about this new work that we're doing with the LISA detector, so space-based interferometer. This is brand new stuff, unpublished, and it's being done within a project in the cosmology research group within LISA, guided by myself. But let's start from the top. What is the stochastic gravitational wave background? So we consider the background to be made up of all those signals which are unresolved by our detectors. So they may be of either astrophysical or cosmological nature. Now, just to brush up on what signals we may be thinking of. So if you're thinking of an astrophysical background, you're talking about gravitational waves that are very low redshift. So typically, you're thinking of compact binary inspirals and mergers. Or you might be thinking of something a little bit more exotic. So people have thought of asymmetric supernovae explosions or gravitational captures or what have you. On the other hand, it's interesting to talk about cosmological backgrounds. So these are going to be gravitational waves that are very high redshift. Now, typically, first thing that comes to mind is gravitational waves generated during and at the exit of inflation. You might be thinking otherwise of phase transitions in the primordial universe, or maybe a cosmic string network that produces a gravitational wave signature. So whatever...
What kind of phase transitions are we talking about?
Electroweak, typically. There are models for... So it's not standard model phase transitions. Yeah. First order electroweak phase transitions. So whatever background you prefer, the focus we decided to take was, let's just consider a stationary background in time. And this will be generated by multiple sources which overlap in the time stream of the detector. So necessarily, they will give rise to an incoherent gravitational wave background. Okay? So necessarily, we're interested in studying the intensity of this background, which is the quantity which will discard the phase information and will average over polarization properties. These signals will be coming from all directions on the sky. So it will then be automatically interesting to study the anisotropies in the background. And as I said before, it's produced by a variety of sources. Okay, so one way we can think of distinguishing between different sources is by looking at how they populate frequency space. Now, on that note, this is a typical plot that gravitational wave people show at the beginning of their slides. So this is how different gravitational wave signatures populate frequency space with some characteristic amplitude on the y-axis. So starting from very low frequencies, roughly nanohertz, you have the typical signature that you might find here is, for example, inspirals from supermassive black holes, which then might merge at slightly higher frequencies. So this is typically referred to as the LISA band. So between 10 to minus 3, 10 to minus 2 hertz is a sensitivity sweet spot. But here, actually, you have a variety of gravitational waves. Okay, so from galactic sources all the way to extragalactic and very high redshift gravitational waves. This is definitely the richest part of frequency space when it comes to gravitational wave detections. And then all the way up here, you have the high frequency regime for gravitational waves. So this is going between 10 to 1,000 hertz, which is probed by the LIGO interferometers, or in general, any interferometer you'll build on Earth. And so here you typically see extragalactic signals, but low redshift, and they'll be burst signals, right? So they're just the merger events of compact binaries. Now, the specific quantity that I'm plotting here on the y-axis is the omega parameter for gravitational waves. Omega, just to parameterize, like you would parameterize any other energy content in the universe, so it's just a fractional energy density. And it's related to the specific intensity of the gravitational waves with this formula. So all I want you to notice is that you've got an f cubed that goes between, converting between the omega parameter for gravitational waves and the intensity. So from now on, I'm really going to be thinking about how to make maps of the intensity of the gravitational wave background. But just bear in mind that you've got this conversion factor if you want to then look at the results in omega. So at the very beginning, I said that we consider the background to be made up of all those signals which are unresolved by the detector. And this kind of makes you think that there is some connection between the background I'm thinking of and the specific detector I want to use to detect it. And that's kind of the point of what we're doing. So this is just a cartoon, intuitive way to sort of get a feeling for what it means to measure backgrounds with different types of detectors. So take, for example, LIGO. And imagine that this blue curve represents the LIGO population statistic. Now we know that we only observe order of few events in LIGO compared to the length of the time stream, okay? So the detection threshold is set quite high. And we know that just below the detection threshold, you're going to have a variety of little almost detections, okay? So there will be a lot of signals that are just below the detection threshold, but are not positively identified as specific merger events, okay? So this will give rise to what we call a shot noise type of background, which is unresolved in the time stream, but it still populates the time stream very sparsely. And only all the way down here will we have a truly continuous unresolved background made up of gravitational waves that are just always on. Whereas on the other side of things, for example, for LISA, so a space-based detector, we expect to have a very low detection threshold, observing many, many signals in the time stream. And so the passage to a continuous background is considered to be rather close. So integrating, so first of all, subtracting carefully your signals on top, and then integrating down, you should be able to access a truly continuous background. So this gives you an idea of how, LIGO resolves very few signals, and so we're going to have a background which is made up of shot noise or popcorn, which is sparse in the time stream, whereas LISA is supposed to resolve many signals, and so we should be able to access a truly continuous background in time. Now, I need a water break, sorry. So 3 years ago, we set out to build an estimator for the gravitational wave background, monopole, and anisotropies. And now, why were we doing this? Well, imagine if you have a map of the astrophysical gravitational wave background. First of all, you could investigate large-scale structure from a completely new perspective compared to electromagnetic signals, and perhaps even investigate polarization properties of the structure. Whereas if you had a map of the cosmological background, you'd be answering a whole different array of questions, including constraining cosmological models, and also perhaps probing fundamental physics. So this is the array of questions we could answer if we had maps of the gravitational wave background. Now, something I like to add, just to keep our eye on the prize, it's guaranteed to be detected in astrophysical background, right? Because we've positively identified gravitational waves from astrophysical signals. The background is in the data. You just need to either wait long enough to integrate down to it, or perhaps build an optimal estimator or a more optimal estimator. So just to be a little bit more specific of what sources we've got on in the different bands, in the LISA band, or we could also refer to it as the space band for now, well, the space-based human-built band. We have, first of all, a very loud galactic background, primarily from white dwarf binaries in our galaxy. And that's expected to be the loudest background in the LISA band. Then outside the galaxy, we expect to have still stellar mass binaries, which produce a confused background just below the galactic one. And then many orders of magnitude below, there are some expectation values for a primordial signature. On the other hand, on Earth, I'm really trying to drive this point home, we have shot noise backgrounds from both black holes and binary neutron stars. And again, orders of magnitude below that, we may have also primordial signatures. I call this the LIGO 3G band. For those of you who are not maybe familiar with what 3G is, this is third generation detectors. They're expected to probe roughly the same range of frequency as LIGO detectors, which is the range accessible to length scales on Earth. But it's expected to be a lot more sensitive. Okay, so it's going to be very interesting to look at backgrounds in 3G because the behavior of the backgrounds in the time domain might be sufficiently different that we might be able to detect them. Now, just to post up here what the current upper limits are to omega GW, I'm reporting here from different collaborations which are looking at different points in frequency space. So here we have the current upper bounds from PTAs, so pulsar timing arrays. These are the pulsars which are probing the very low frequencies, so nanohertz. These are numbers from the Nanograv collaboration. And then here we have the upper bounds from the LIGO collaboration, so using the LIGO Hanford and LIGO Livingston detectors. And down here, I thought I'd just also post our current upper bounds. So the upper bounds that we've estimated are estimated using the very same data as the LIGO detectors. And in fact, these numbers are in very good agreement, right? So this is very encouraging. So for the rest of the talk, what I'm going to do is I'm going to tell you how we obtained these numbers, and then I'm also going to show the maps that go with them. So this is what our pipeline looks like. We start from either real LIGO data, so thankfully LIGO provides open access data which we can just take home and analyze. Or on the other hand, we also simulate data, and this is just as a proof of concept, just to make sure that our mapping algorithm actually works. So if we start from the real data, we have to clean it, filter it, and do some selection on making sure that we don't have any bad segments that we're analyzing. Or on the other hand, if we're simulating, we need to first simulate a map that we want to reconstruct, simulate the response of the detector, but also simulate the noise that has to go with it. Now, whether you have real or simulated data, they both get fed into the estimator part of our pipeline. So this is where we extract the optimal map given the data with a maximum likelihood method. So at the end of the day, we're left with a map of the gravitational wave backgrounds anisotropies on the sky. Now, for those of you who maybe are familiar with some of the jargon and have heard of gravitational wave background mapping before, just to set our method aside for a little bit, there are other methods. Some of them use constraints which make them particularly efficient, like sidereal folding, for example, which is highly efficient for ground-based detectors, or just alternative approaches right off the bat. So for example, you may be interested in a coherent approach, whereas we're working with an incoherent approach. We're just integrating over all angles, or radiometer maps. Okay, that's a completely different approach from what we're doing. So what we do is most similar to the spherical harmonic decomposition approach, but we're also borrowing some tools from CMB data analysis. So the keywords that I kind of like to stick on to our method is we're working in Pixelspace and in sky coordinates, which allows us to have a generalized pointing solution on the sky. This means that we're not fixed to any particular detector frame. Okay, specifically, we'll be looking at maps in the frame of the galaxy. We try to reconstruct any type of signal. Okay, so we make no assumption about what signal we're reconstructing. But to do this specifically, we really need to use long integration times, as much time as the data allows. So we built this pipeline with a bottom-up approach. We started from the real LIGO data and tried to figure out how to get a map out of it. But the approach itself is utterly general. So after that, we set off to port it to other detectors. And that's why at the end of the talk, I'm also going to talk about LISA.
What is sidereal fold?
It's basically if you have two detectors on Earth, so one baseline, you can assume that the passage of time, it's like a day, is just a phase on the sky. So you can repackage your data by just saying, this time today integrates over this time tomorrow and tomorrow and tomorrow. So you just fold a year, for example, into a day by compactifying the data.
And what does radiometry map have anything to do with the gravity wave type?
So radiometer method is trying, so as I will say in just about a few minutes, the beam on the sky for gravitational wave detectors is not compact at all. We are sensitive to all directions on the sky in different ways, which is, of course, key to our mapping procedure. But essentially, it's not compact. What these guys do is they compactify it by just adding a delta function, convolving a delta function in the time domain. It's a little bit like cheating, if you will, but it's, no, sorry, I shouldn't have said, I'm even being recorded, oh my God. No, it's because you assume you're trying to reconstruct a specific signal. So you're saying, I want to say, oh, you know, I know that in that direction there's a galaxy. I want to see if there's some surplus of signal coming from that galaxy. Let me just put a delta function there and see if I get an above 3 sigma type signal. So that's kind of the idea, the philosophy. That's why I really, oh no, you see? See what you did? That's why I push this idea, right? So reconstructing any type of signal means I'm not assuming that my signal is coming from galaxies. I'm just trying to reconstruct everything without being too biased about what it is. Yeah. So if I lost you at spherical harmonic, let me just make sure that we're all on the same page here. So when I talk about pixel space, I think this is rather intuitive. It's probably what all of you are thinking of right now. I have the 4 pi on the sky. I divide it into equal area patches. I number the patches, and then I try to estimate a number, say an intensity or a temperature in each of the patches, and then I'm left with a map. I might do this in spherical harmonic space. So I estimate the spherical harmonic coefficients of my signal. So decomposing my signal into spherical harmonics, as you can see, or maybe not so well. You could see it when it was playing, right? So you see, as we go up in L max in my spherical harmonic expansion, I recover a resolution on the sky. Okay? And then, so I can work in spherical harmonic space and just port back to pixel space at the very end, just for representative purposes of looking at a map. So you can see that there's this direct relation between the number of pixels I'm using on one hand and the maximum L to which I'm expanding the spherical harmonic space on the other. And you feel like this should be a completely transparent relationship. In a sense it is, but what we found for gravitational wave background mapping is that working in pixel space is, on one hand, more straightforward, but essentially gives rise to a better conditioned problem. Now, this is a bit technical, and I would get really bogged down if I went into the details, so please do ask me at the end of the talk if you're really interested. But the take-home message is that, in the end, the conditioning that we get and the constraints that we get are a little more stringent. So without further ado, let's dive into the pipeline. So the first bit we do, if we're using real data, is we have to clean it up a little bit. So if you look over here, this is what the data looks like in the time domain. This is a minute of data. In blue, you have the Hanford gravitational wave detector. And in orange, you've got Livingston. So you see they're doing their thing. And the only thing we do in the time domain, really, is we select coincident data segments. And we segment them into 60-second chunks. OK? Everything else we do in the frequency domain. So we FFT. And we look at the data in frequency space. Here, we high and low pass. So we're only looking at this section of the data in frequency, between 30 and 500 hertz. And this is where the sweet spot of the LIGO interferometers is. Then we notch out certain frequency values, which we know are just sources of noise for the LIGO detectors. OK. And then this is a really important bit. We fit a parametric curve to the power spectrum density of each segment for both LIGO detectors. Okay, so this is the red dashed line that you can see here, and we're going to be using this line later on. So maybe hold on to it in your head because we're going to use it to create the optimal estimator. Now, at the end of this, what we have is we have two data streams for two detectors. They are coincident in time in the frequency domain, and we've cleaned them up so that we know we can use them. But we know that in the LIGO detector specifically, the noise is overwhelming. Okay, so what we can do to try to beat down the noise is we cross-correlate in frequency, so between the two detectors. And so what we end up with is a single data vector for the Hanford-Livingston pair, specifically for LIGO, which is constructed by just taking the cross-correlation of the data in Hanford and the data in Livingston.
So is there a correction there for the increased noise? So in your plot here, right, Livingston is much less noisy than Hanford in this plot, in this way that you chose. So when you make this cross-correlation here, do you have to correct for that, or you just don't care?
No, we don't care, yeah. I think you'd care more if you were doing a resolved detection, right? But for this method, it downweights itself. And it's true that it's a bit noisier, but actually the threshold is pretty much the same. As in, it will be downweighted by how much it's noisier. So it ends up being, yeah. Thank you. So instead, if we're working with simulated data, let me just take you through steps of what that entails. So right outside our gravitational wave detector, we have a gravitational wave. So if it's a gravitational wave background, we can just expand it into its plane wave expansion. So that's what we're doing here. So the strain of the gravitational wave just outside the detector is going to be some integral over the sky. We're also summing over polarization components because we've decomposed the strain into plus and cross components. So that's H plus and H cross. So it's weighted by its own polarization basis component. And then you've got your plane wave factor here. When it enters the detector, what happens physically is like a projection, right? So your gravitational wave is projected on the arms of the detector. And mathematically, the way we do this is we contract the polarization tensor with the response of the detector, so the polarization response of the detector. And that's how we're left with the polarization response functions f. So f is going to be dependent on polarization, so f plus and f cross will be what we're summing over here. And then this gives us, in the end, the strain measured by the detector. So f is, they're functions that depend entirely on the geometry of the detectors. Okay, so the fact that they're L-shaped and where they are on Earth with respect to the background we're measuring. But as before we cross-correlated the data streams in frequency space, we need to do much in the same. So if we have two detectors, let's say detector I and detector J, and we just want a single data vector SF, we cross-correlate and we're left with equation 3. So under the directional integral, we have the intensity of the gravitational waves, and ta-da, this is exactly what I want to make maps of. So really the name of the game is going to be inverting this equation. But the intensity of gravitational waves on the sky is being weighted by the overlap function. Now, the overlap function is some combination of the response functions we were looking at before. It's going to be directional, so it's going to be different in various directions on the sky. And I'm introducing a new name here. Instead of calling it, let's say, the overlap function of detectors I and J, I'm just calling it the overlap function of B, the baseline B. So the baseline is just the vector that connects the two detectors I and J. And effectively, the properties of the overlap function depend entirely on the relative position and configuration of the two interferometers. So it's well encapsulated in this length scale of the baseline. And in fact, it'll be the key length scale for map making. Moreover, because we're not working in a specific setup where the positions of the detectors are constant, the baseline vector will be pointing at different directions in different times. So this is sort of the idea that goes behind map making, but this will become clear in a second. So effectively, the way we generate this is we generate a single map for the intensity background, which is what we want to make, what we want to reconstruct at the end of the day, feed it into here, and we're left with a correlated data vector in frequency space.
So is that function the thing that captures the delay between the
Yeah. Exactly. So the baseline, the length of the baseline is some sort of optical length, right? Like which kind of encapsulates the phase difference that goes between arriving first in one and then in the other, right? So that length scale appears here, which is this exponential term basically encapsulates that delay. So I've just taken you through how we construct the signal component. However, that's not the end of the story, especially if we're thinking of the LIGO detectors. So we also need to make sure that we're adding the noise contribution to our overall simulated data. So I'm going to fish back for the red dashed line, which we fitted to each minute of each LIGO detector to get an estimate for the noise. And what we do is we just randomize around the PSD of each segment, and we get a noise contribution which we can add on to the signal and get simulated data. So this is done for every minute of the LIGO data. So we really simulate going in parallel with LIGO using the same noise curve. And the simulated data changes minute by minute because our sampling of the sky is changing, and this is encapsulated in the response function. So as the vector B, the baseline, points at different directions, the response of our setup is different, and that's how we kind of piece together a map. So to have an idea visually of how this works, this is what the response function looks like for a moment in time. Okay, so you can see that there's a hot direction on the sky, and it's the the amplitude of this is quite washed out, so it's a rather broad beam or non-compact. And then we have some quiet directions, which, if I'm not mistaken, are perpendicular to this one. But then if I let time go by, I see that I'm sampling the sky in different ways at different times. So by kind of shining the flashlight in different directions as the Earth goes around, I can piece together a map. And that's exactly what we do. So
what does negative response mean?
it's just highly downweighted. So it's like it turns out to be like a 0 in your response, but it's just the offset is set such that you have a negative response and a positive response. But at the end of the day, this is integrated. Sorry, this is integrated over the whole sky in your time stream. So it's like these are just, it's like a 0. It turns out, it translates into like a 0 for effective purposes. So I do not see anything coming from here.
So, sorry, so the negative is just around the average antenna factor. Like if you average the antenna factor over the whole sky.
Exactly.
Okay.
Yeah. All right. So whether we started from the real data or the simulated data, the estimation of the optimal map is the same. So all we're using is maximum likelihood method, which just entails minimizing a chi-square, which is this guy. It's nothing particularly new. It's been used in gravitational waves before. It's been used in CMB way before that. So we're not doing anything particularly controversial by taking this. The only real thing I want to point out here is what our noise estimate is. So the noise that you see here in the construction of the chi-square is literally those red curves that I was showing you before. So it's just the cross correlation of the power spectra in the LIGO detectors minute by minute. So this gives us an optimal estimate of the noise, and this is because the noise in LIGO is not biased by any signal. So this will be essentially different for LISA, which will need a completely parallel noise estimation method before we can even start thinking of doing mapping. So by minimizing the chi-square with respect to the map that I want to extract, at the end of the day, I end up with equation 8. Just look at 8. So the intensity of gravitational waves as a function of pixels, so my n and m's here are pixels on the sky, is the result of this operation. So we are inverting an operator which we refer to as the beam pattern matrix and applying it to what we call the projection operator. Now, this is the trickier part of the talk and perhaps boring for some, so I apologize in advance, but there are just a few things I want to say about these operators which I think can encapsulate sort of the key elements of how the mapping procedure works, so bear with me. The projection is quite literally taking the data in frequency space and projecting it onto the sky. Okay, so here you see your data vector as a function of frequency. And then you're projecting it by using this response operator A, which encoded inside is the overlap function. So it's like taking the overlap function for 1 minute and projecting the data in frequency space onto the sky. But you're doing this by also weighting by the noise in that particular data segment. You then wrap it up by integrating over the frequency band that you've decided to consider, and then you average over all the time that you have available, and say you also have extra detectors, so you have more baselines on Earth, you can also average over all those baselines. The beam pattern matrix instead is constructed by just taking it's like the cross-pixel correlation matrix, okay? It's telling you how one pixel is doing with respect to another. So you take effectively the cross-correlation of the response operators A, so the gamma function, say, in 2 different pixels, and then again you weighted by the noise. You integrate again over frequency, and then you average over the times and over the baselines to continuously update what your estimate for the beam pattern function is. So in the end, you get this intensity map, and you can see these operators are running integrals over time. So this intensity map is continuously updated and continuously goes towards its optimal value. Now, you may have noticed that this calculation entails a direct inversion of the beam pattern matrix. And in fact, this is the trickier part of the whole estimation, because the beam pattern matrix is highly singular, and so it's not straightforward to invert. The reason why it's singular is quite intuitive. If you think about it, you're only sampling, at a given minute, you're only sampling very specific directions of the sky, and then most of the sky is invisible to you. Those translate into zero eigenvectors of your matrix, so you can't invert it. So necessarily, you can try to cure this by either looking at different directions at once, which for us translates into adding more and more baselines on Earth. So you're sampling different directions simultaneously and then solving your degeneracy in the beam pattern. Or you can integrate over long periods of time. So if you wait long enough, hopefully you'll hit all the modes on the sky, and then you'll be able to invert your beam pattern. So now I'm going to tell you about the 2 applications that we've run our code through. One is simulating data. So this is just a proof of concept that the method actually works. And the other is by analyzing all of LIGO's open data and see if we can estimate a background with the LIGO data. So let's start from the first one. So this is refers to our methods paper, which is the first publication we put out for this work. So let's just take the Earth and rotate it into galaxy coordinates. This is what the baseline looks like in this frame. So here we have LIGO Livingston, LIGO Hanford, and let's imagine we also had Virgo online, okay? So effectively what we're doing is we're simulating data for these separate baselines and trying to reconstruct a map. So, so here on the left-hand side, we have the maps we're putting in at 2 separate and different signal-to-noise regimes. So let's say we input a map that is roughly 0.9 times the amplitude of which is roughly 0.9 times the noise. Okay, so let's say it's almost 1. It's almost at the same level of the noise. And down here, instead, we're putting it almost an order of magnitude below the noise. And this is just like the initial comparative level between the input map and the noise that we've got in the detectors. And if I press play, you can see that as time goes by, I'm integrating. And you see the top map converges almost right away. Right? This looks pretty close to the map I put in. Whereas the bottom map, which has a lower signal-to-noise regime, it's coming out. I mean, the hot and cold spots are roughly in the right places, but you can see there's a little bit of ringing and there's some noise. So this was only a day. This was only integrating over a day of data for the 3 baselines I'm simulating for. So if we'd waited a little bit longer, probably this map would have also smoothed out.
Back to the method in which, one of the standard things to do is to do this by Wiener filtering as opposed to just using the inverse. And an advantage of that is that it would solve all of the problems of having incomplete coverage. And so what that would mean is that it's actually a full reproduction of the statistics. It's just that the covariance matrix becomes maybe a little bit more complicated, but it does have the advantage of being associated with some sort of beginning as opposed to a blank sky with no information. Have you looked at that at all?
We haven't. We started off worrying that we wouldn't be able to invert the matrix, and so we kind of had in mind that at some point we would have to worry of going into some more sophisticated way, and I've definitely heard of Wiener filtering, but the point is that because, so for one, the beam is so non-compact, and for the other, LIGO really is sampling very efficiently, if you will, because because you get a full 360 in a day, and you have many, many days over which to average. So effectively, the conditioning gets better very quickly, and you can invert it. You can outright invert it almost after just a handful of days. So it just seemed like it wasn't necessary to do this extra leg of work because it came out to be quite well conditioned.
Is that because you're looking at the stochastic background as opposed to some very short transient signal, you have to integrate over a very long amount of time, which causes the computational expense to become unfeasible. In addition to that, Wiener filtering requires that you know the precise time evolution of the phase of the signal. Whereas in the stochastic background, because that's altered multiples.
Well, it's, okay. One might wonder that if it's a true stochastic background, it goes in the central limit to something else.
But that doesn't change the fact that the precise phase information of the time-domain signal that's required for Wiener filtering needs to be known in order to apply that method. Sorry.
No, that's all right. I may run a little bit over time, just FYI. Right, so if you want to look at this numerically, and this kind of goes in the direction of the question I just had, you can look at how the conditioning evolves for the beam pattern matrix as a function of time. So this is just one day. And you can see that if you only have one baseline, so there's specifically the LIGO baseline, your conditioning is stuck up here, so it's unconditioned, and so I can't really invert it throughout, let's say, the first 12 hours of the day, but then it starts getting better. Now, here the point I was making is actually that if you add a baseline, so for example, for the 3 baseline case, which is the one I just showed you the results for, the conditioning gets better right away, so even within the single day, and very quickly, and then kind of plateaus down here. So you can really see the benefit of sampling different directions on the sky simultaneously. And then you can also kind of see how this converges, sort of, because if you add, like here I'm showing you a 10 baseline case where I've added actually 2 more detectors, and you see the conditioning is better, but it's not in any way that much better compared to how the 3 baseline was going. So you can see you saturate the conditioning of the beam pattern quite quickly. So the upshot of this is you definitely want 3 detectors compared to 2, but I'm not asking for 10 detectors. It's something that we can do with the detectors that are planned for the near future.
Did you optimally place the G detector? I'm assuming that these
No.
are like LIGO, Virgo,
Did not.
Cagra.
Yeah. So these are Livingston, Hanford, Virgo, Cagra, Geo. So no. Yep, I left these where they are. I just assumed that they were as good as LIGO. So that is obviously a big assumption. But with LIGO India coming up and Cagra, you'll get something that if you substitute Geo with LIGO India, you actually get something which is a lot better. So the other thing I wanted to say is just how the standard deviation of the maps evolves as a function of time. So this is just if you will, not as entertaining way of looking at the videos I was showing you before. So how quickly do I converge to the map I put in? And you can see that if I put a high signal to noise regime in, it just converges right away. You can have different signal to noise regimes which converge later, all the way to something which is low. You can see it hasn't converged, but it's going down as 1/√t. And this is exactly the evolution that I expect it to have, to the point where if I inject a background and I know the amplitude, I know how long it's going to take for it to converge, so I can run some diagnostics on that. I'm going to skip this over because I don't want to run out of time. So which takes us to the other analysis we've done. So we analyzed the full advanced LIGO 01 and 02 data sets. These are openly available on the LIGO website if you want to have a look. The way we do this is by searching for a specific background signature in the data. So you may remember the optimal map estimation involves an integral over frequencies, okay? So effectively what we need to do is we need to assume a spectral shape for the background if we want to do this consistently. So this translates into 3 different searches depending on what spectral shape we assume for our background. So what we're doing is we just, well, let's say we know what the spectral dependence of the intensity for gravitational waves is. It'll be some sort of power law like this. So what we search for is a typically referred to as cosmological background. So you just assume that it has a flat spectral dependence in omega, which translates into f⁻³ in intensity. An in-spiral dominated background, which is typically modeled as having an f⁻² in omega. And then we also do this final one, which I would refer to as the optimal background. This is just, it's flat in the intensity, which is the spectral shape that the data for LIGO has. And so it's sort of the best fitting background for specifically the LIGO case. So these are what our maps look like. So up top, we have signal to noise ratio maps. The first thing that should jump to your eyes is there is no detection. So we're hovering around -2 and +2 signal to noise. So yeah, there's nothing in there, which was predictable. And you can see that the distribution of, this is noise effectively, on the sky is slightly different depending on what spectral filter you're using. But at this stage, what's kind of most interesting, specifically because you don't have any detection, is these bottom maps. These are the noise distribution maps. They're telling you how the noise is distributed on the sky for the 3 different spectral filters. And you see it's very different. You have very different filtering depending on what shape you have. So this is actually very interesting work, and it'll be really interesting to look at this with Lisa, because it'll tell you what areas on the sky are you most sensitive to, depending on what frequencies you're probing. Okay? This is really telling you how the modes in the noise couple to the directions on the sky. Now, I think this is the final slide on LIGO. So I guess this is maybe the most significant plot in our latest publication. This is just how long to go, right? How long do we have to wait to actually get a detection of the astrophysical background? So here you have the current estimates, the current model for an astrophysical gravitational wave background. So this, you can see this is an f⁻² in the omega parameter. And this is our upper limit. This orange dashed line is our current upper limit in the LIGO frequency band. So you see it's just shy of an order of magnitude before it scratches the surface of the current estimates for the background. So that should mean probably integrating 100 more years of LIGO data at the current sensitivity levels. However, the upgrades that are planned for the LIGO detectors should put us just around this area. So we should just about scratch the surface of the current estimates once we get to the design LIGO sensitivity. Now, with the time that I have left, I'm gonna tell you a little bit about Lisa.
Like 10 minutes?
Yeah, I just fly. So LIGO Lisa, is there a big difference? Okay, so just to refresh everyone, LIGO, it looks like something like this, right? So you have 2 4-kilometer arm orthogonal L-shaped detectors in Northern America. So one is in Hanford and one is in Livingston. And this baseline is about 4,000 kilometers. So to a good degree, you can kind of assume that the noise is uncorrelated between these two detectors. And that's what we do to sort of beat down the noise at first order. On the other hand, LISA is a whole different cake, right? So you have 3 spacecrafts in space, necessarily, in an equilateral triangle configuration. And each arm you can imagine be made up of 2 links. So this is a laser beam going in this direction, and this is a laser beam going in the opposite direction. So you can imagine that whatever, let's say, Michelson-Morley style interferometer you can build with LISA, so something that interferes light going one way with the light going the other way, will share an arm, or in general will share noise. So whatever detectors you can construct with the LISA spacecrafts will be correlated in noise. Okay, we'll share some noise. Now we can say this a little bit more efficiently, like so. So let's say this is our data model. Our data has some signal component and some noise component, and we want to extract the optimal map, just like we did before, by minimizing this chi-square. But the chi-square, this method only works if the noise is mean 0 in the data model, which we kind of assumed for LIGO. Like we literally assumed for LIGO, okay? We were just assuming that the cross correlation of the noise for Hanford and Livingston on average, or rather ensemble average, was 0, which is really not the case for LISA, right? We know this for a fact. The trick that we thought we'd use, though, is that the noise in frequency space should be white. Now, we can debate this, but let's say can be whitened. Okay, so we can assume that we have a noise model for which we can whiten the noise, and so we can take the D here, instead of taking the cross correlation of the strains, is just literally the strain measured by a single detector that we can construct with LISA. Now, speaking of detectors with LISA, let me just tell you a little bit about time-delayed interferometry configuration. Now, this is important just to have an idea of what I mean by the detectors in LISA. So if I have 3 spacecrafts, 1, 2, and 3, well, the Michelson-Morley style interferometer I can think of is this thing where I interfere the round trip of light between spacecraft 1 and 2 with the round trip of light with spacecraft 1 and 3. And this is typically referred to as time-delayed interferometry 1. TDI1 configuration. You can do something a little bit more sophisticated, which is you interfere the round trip between 1 and 2 and 1 and 3 with the round trip done in the other direction, and this gives you TDI 1.5. But at the end of the day, what this leaves you is you have 3 channels, 3 TDI channels, typically labeled X, Y, and Z, and these correspond to 3 correlated detectors. So how do we construct the data? This is exactly the same slide I showed you before. I'm not going to lie. The only difference is that now the response function is not the response function of a detector which is independent from the other, but it's a response function that is specific to a TDI configuration within LISA. Okay, so it's going to be sensitive to frequency and direction in a very specific way. Whereas the noise construction is a little bit trickier, right? So the noise is correlated in the XYZ channels. So we need to generate a noise vector which encapsulates this correlation. So what we do is we generate a noise vector as a realization of the theoretical cross-power spectrum. So we have a model of what the cross-power spectrum should look like. And what we do is we actually generate a noise vector in the noise diagonal space, and then we rotate back to correlated space by just borrowing the eigenvector matrix for the noise model. And then, of course, we can mimic high and low signal-to-noise regimes just by jiggling about the amplitude of these noise vectors. Now, to understand how we make the maps, just like we did with LIGO, we want to look at how the sky response for the LISA TDI channels looks like. So we're working in the solar system barycenter frame now. So again, the 3 spacecrafts are going to be moving in this frame, and the response is going to depend on how they're moving, so x is a function of time. What we're doing is we're generating the data for the 3 TDI channels. Instead of doing once every day, instead of doing once a minute, we're doing once a day, which sets our minimum frequency to around 10 to the minus 5 hertz. And our resolution to which we're working is set by just considering that the response of the detector needs to be roughly constant throughout the whole day for which we're simulating. So if we look at how the response of the TDI channel X to plus and cross is as a function of time, we get these movies, which are pretty trippy also because in here you have a projection, an ulterior projection on the detector plane, which is a 60-degree angle with the ecliptic. So these are not entirely transparent. It's not entirely clear what's going on. So I feel like this is a better movie to show to get an idea of what Lisa is doing. So this is the autocorrelated response for TDI-X. And you can see that just like with LIGO, we have a hot direction, a direction to which we're most sensitive to. And this lies constantly throughout the year at a 30-degree angle with the ecliptic, which corresponds to the perpendicular direction to the plane of the detector. You've got the detector at a 60-degree angle. The perpendicular is going to be at a 30-degree offset with the ecliptic. And then you have your sinks, your quiet directions, which correspond roughly to the directions of the arms. The other interesting dependence to look at specifically for Lisa is how the response function changes as a function of frequency. Now, we didn't need to do this with LIGO because we were in the low frequency limit with LIGO, but with Lisa, it's a whole other chapter. So let's look again at the autocorrelated response, but now we're varying the frequency. So we're going up in frequency, and what you see is that on the sky, the shape changes dramatically. There's two main things that you want to keep in mind. One, we're becoming quieter. We're losing some sensitivity here. It's like the signal is just fading out. But, and essentially for mapping, this is a big but, we're kind of going at a higher resolution, right? It seems like we can resolve very highly in L on the sky if we go to high enough frequency. So there's an interplay between what frequency I'm making a map at and what resolution I'm going to have. You'll see in a minute. So we're back to the chi-square, okay? We want to minimize the chi-square just like we did before. Now, there's just a few key differences. Our data vectors now are linear in the strain. They're not quadratic. And essentially, these are data vectors in TDI space. I'm going to have a data component for X, for Y, and for Z, which are the three TDI channels. So my noise is going to be a noise matrix in TDI space. And so I'm constructing the scalar by taking the contraction of my two data vectors and the noise matrix in the middle. And if I minimize it, I get optimal map solutions for H plus and H cross. Here I'm just running over a generalized pixel index just to compactify them. So this P, curly P, runs over twice the number of pixels. But effectively, I could show you independent maps for the H plus and H cross component of my signal. So we run with that, and we simulate the data. So we're using TDI 1.5 configuration, so the response functions for TDI 1.5. And we simulate for the three configurations X, Y, and Z, and carry out our estimation. And this is what we get. Dramatic pause. All right, so we inject total intensity on the sky that looks like this. So this is just a realization of an L squared CL flat intensity. I'm showing you the intensity, so the squares of H plus and H cross, but I actually inject H plus and H cross independently. It's just for a matter of space that I'm doing this. And you can see these are the maps that we obtain out. And you see how they change depending on what frequency I'm integrating out to. So these guys are obtained by integrating over frequency bands, and depending on what maximum frequency I'm integrating to, I get a different map. So specifically, if I integrate out 10 to minus 2 hertz, this is the frequency I start seeing some structure in my response function. I get a very good fit. This looks very much like the map I put in. I didn't want to lie, so I didn't even smooth them like I did for LIGO, okay? So this is a very close cut with the input map, but I lose that resolution very quickly as I go down in upper limit of frequency. You can see all the way to 10 to minus 4 hertz, I just have these two blobs. They're in the right place, right? You can see that they correspond to where the hot and cold spots are for the input map, but all of the structure has been washed out. You can say this better with a simulation. So effectively what I did here is I simulated this for 200 realizations of an L squared CL flat intensity in input. And you can see here the gray dashed line is the input model, and my blue curve here is my reconstruction of the CL modes, and for the 10 to minus 2 hertz Fmax integration. So we're doing pretty well up until here's the money number L equals 10. And then we start having some aliasing, some ringing, some things that we may want to be thinking about a little bit more carefully. But for now, you can kind of cite an L equals 10 as an upper bound if you're integrating out to 10 to minus 2 hertz in frequency. And then we lose structure very quickly if we're going down in frequency. Another kind of way of turning this plot on its head is you can take the effective transfer function. So you're just dividing the gray dashed line by whatever reconstruction you have here. So you can see this kind of is a bit less sort of, it has no mercy. So it really shows you how much you're aliasing here, and then how much you're ringing up here at high L's. So don't trust it, right? Don't trust it above L max equals 10. However, it might be something that we can cure because this has to do with the conditioning of the beam pattern matrix. Okay, so by conditioning this more carefully, we might be able to straighten this out. So I'm just going to leave you with our next steps. So on the ground-based side of things, the analysis code seems to be working, so we're going to keep analyzing the data and integrating the new upgraded data and hopefully obtain a detection as soon as sensitivity permits. But we're also going to look at the new upcoming networks, so hopefully start filling in some gaps on the sky with more baselines and extend this to 3G. 3G is going to be really interesting to look at because of the sensitivity upgrade. And for LISA, hopefully I've made a case that, the beam pattern matrix is interesting to study, and it will really tell us how the noise modes couple to the scales on the sky. So watch the space. We're going to add in realistic noise and signals very soon. And I think the final challenge that we want to look at before putting these results out there is to get to test this on the LISA data challenge data and see whether we can get a map of the galactic binary background out.
The 10 minus 2 hertz is basically the inverse of the light travel time between different nodes of the LISA.
No, sorry, could you say that again?
The 10 minus 2 hertz.
Yeah.
It's basically the inverse of the light travel.
No, it's a bit lower than that. So it's not too optimistic for LISA. It's roughly, it's when you start getting the ringing effects. Yes, I see what you mean. Yeah. So maybe I could borrow. So if you look at what the LISA sensitivity curves look like, wow. You get this. This is roughly 10 to minus 2 hertz. Actually, this is 10 to minus 2 hertz. This is 10 to minus 3. This is 10 to minus 2 hertz, like here. And then here, you start getting those ringing effects. And these occur exactly when you say, so when your frequency is the characteristic frequency of the detector. So it's, in length scales, it's the length of the arm of the detector. So in fact, this is what you're seeing. It's the effect of this modulation in the sensitivity that you're seeing when your response on the sky as a function of frequency changes. So it's the fact that if you're looking at the detector arm, you have a wave that just about fits in the arm. Then you start having waves that go out, and then you have a wave that is exactly double the arm, and so you get a peak, and so on.
Good. Can you hear a question? Then we have Art.
So I'm very curious about whether or not, my brain is not working, whether or not you think that we can smartly get at higher L's for lower frequencies, because the gravitational wave foreground from double white dwarfs drops off well before 10 to the minus 2 hertz.
Yeah, so that is our biggest preoccupation currently. That is why we make a case that we need 2 LISAs.
Okay.
Yeah, no.
Punchline way to make it better, and the answer to LISA.
No, yeah, the answer is 2 LISAs. So do not get too disheartened. I mean, if we if we were working at this, okay, you'd still see a circle. You know, it would be very unresolved. You wouldn't be doing precision cosmology or precision astrophysics with it, but you'd definitely be able to tell what's on the galaxy and then what's not on the galaxy. So specifically for people that are motivated by cosmological backgrounds like myself, I can tell you, well, whatever's not on the galaxy, which will be, you know, in the solar system barrier center frame, just a circle on the sky, I can tell you that what comes from here and what comes from here will be not the galaxy, which could then be a cosmological source, right? But yeah, what we will be able to look at like this maybe is the resolved galactic binaries. Yeah.
Let's take one more question. Yeah, thanks for this great talk. I was really interested in what you said about the noise modes being coupled in the LIGO.
Yeah.
Coupled to different noise by frequencies being coupled to different directions in the sky.
Yeah. So I wish I had put some other plots in here. So this is you know, if you look at, sorry, I'm going to try to motivate it mathematically. If you look at this guy, yeah, maybe. No, actually, no. So, okay, so it's not specifically from here, but let me just make a case sort of by thinking about it out loud. So you're going to have terms where you have a coupling between a frequency, which is the frequency of your incoming wave, and then a direction on the sky. So like in this case, the baseline the direction in which the baseline is pointing to. And you're going to have different modes in the noise at different frequencies. Okay, so these are going to couple to the directions on the sky depending on what amplitude they have at that frequency. So what you're looking at here, what you're looking at here is alpha equals 0. Alpha equals 0 in intensity means a sharp f-cubed slope. So we're killing off all of the high frequency modes. So this is just low frequency noise. Low frequency noise is going to couple to these particular directions on the sky. And it turns out, you know, when Carlo looked at it the first time, he said, oh, look, this is the ecliptic. I'm not 100% sure that's true, actually. But yeah, you might think, oh, maybe there's some offset given by the solar system or something. So that's what I mean by a coupling between the frequency modes in the noise and the scales on the sky. The interesting thing is if you compare it to this guy, which is flat, and because the high frequency noise is dominating in the wedge of frequency space we're looking at for LIGO, this is actually all high frequency noise, right? Including this really hot mode here for some reason. So this is actually telling you how the high frequency noise is behaving. The reason why I said I wish I had put other slides in here is because in one of my extras, I have one of the other analyses we've done. So we've done a frequency binning unbiased approach to the problem. So we made different maps in the different frequency bins to see whether we got different maps for the gravitational wave background depending on what frequency portion we were looking at in the LIGO band. And so I actually have the noise maps in these different frequency bins. Okay, and here you see it even more. On one hand, it doesn't look so smooth. I realize it looks really smooth in the maps I showed you before, but that's an effect of the integration over all the frequencies.
Okay, so if there are any more questions, let's say them for cookies or for dinner. We're going to Hawktown Vegan. There's still one or two places, so feel free to join. Now let's thank Arianna one more time.